we will now look at these things about electron distributions around central atoms when they form bonds, the types of shapes that gives rise to, and the polarity of bonds and whether molecules are polar or not. Again, something that there's lots of questions about in exams. Okay, I don't think you can see me. I've got the camera on, but anyway, a couple of people typing now. Let me see what they've got to say. I've looked at tetrahedral shapes, but not anything larger yet. Okay, because the tetrahedral shape, don't forget, was in your level 2 work. Okay, so this is an extension of that. Good. So I think you'll be able to follow it without too many difficulties. The others seem to have done that. Let me go over to the next slide, where I've actually put these geometries of different things. Let's go through it quickly first and then apply it with these examples. Geometry of simple molecules and ions in which the central atom has one or more lone electron pairs. Now, this is like the lone electron pairs, number of bonding pairs. The B is the number of bonding pairs. E is the number of lone electron pairs, and the total number of electron pairs is there. If you have 3 electron pairs around something, what's the way that you can separate them? I'm talking about 3 electron pairs. I'm not concerned with if they are bonding or non-bonding. But if you have 3 electron pairs, the way you can separate them the most is by this sort of a trigonal planar arrangement or planar triangular arrangement with 120-degree angles. That's when you have 3 pairs of things. If you have 4 pairs, then it's this 3-dimensional tetrahedral arrangement where these are just geometric facts, okay? I'm not drawing this very well, but remember these 3-dimensional, and you've seen the type of structure that this refers to, so you'll know what I mean. That bond angle there in a perfect tetrahedron is 109 degrees and 28 minutes. There. Okay. That's a trigonal planar or a tetrahedral arrangement. Then, of course, if you have just 2 electron pairs that you want to separate to a maximum, 2 bonding electron pairs like that on either side of a central atom, naturally the angle will be 180 degrees. And there we have it. Okay. Now, when you come to more than 4 electron pairs, which is in this, oh, by the way, just for completeness of what we are talking about, I messed that up more than trying to make it clearer there, but making those lines thicker. If one of these electron pairs is, or one or more, is a non-bonding electron pair, if it's not shared between 2 atoms, then what happens is, remember, the nuclei are positive, whereas the electrons are negative. So if the electrons are not bonding between 2 atoms, then those electrons are not drawn tightly towards the axis between the 2 atoms. Right? What I mean by that is this. If you have a nucleus that has a positive charge here and a nucleus there, a bonding electron pair will spend a lot of its time in that region between the 2 positively charged nuclei because it's being pulled by both of these positively charged nuclei. So a bonding electron pair is held tightly. It's sort of like having a balloon that 2 people are grabbing at. It won't be as fat in the middle, it'll be elongated and close to the axis between the 2. But on the other hand, a non-bonding electron pair, let's say that belongs to this particular atom that I'm drawing with a positive charge, it will be only drawn to 1 nucleus, so it's going to be puffier, bit like the head of an octopus. That's like an electron pair. And let me just draw this one here a bit better. There we are. And we draw it sort of like this. Okay. It's puffier. What I want you to get is the difference between this sort of situation and that sort of situation. A lone electron pair, or also called a non-bonding electron pair, occupies more space. It's puffier. A bonding electron pair is drawn tightly towards both nuclei, so it's going to occupy a small space there. So the bond is much closer to the bond axis. It's not as puffy. So when you have this here, this is how you end up getting a pyramidal shape, like with an ammonia molecule, for instance. I'm talking here at the moment about stuff that you have really done in your level 2 work. There. And that angle here is less than this angle, for instance, here, okay, is less than 109 degrees, 28 minutes. Why? Due to this lone electron pair on the nitrogen atom occupying a bigger space around it, compared to these 3 bonding electron pairs. So the 3 bonding electron pairs get squashed a bit like that. And for similar reasons, when you have a water molecule here, it starts off, you can think of it, the structure around the distribution of electron pairs around the oxygen as being tetrahedral, right? There's 1 electron pair and another electron pair. But what happens? The net result is that we end up with 3 centers here, the hydrogen, the oxygen, the hydrogen. And this is a distortion of the tetrahedron. So we end up with this bent shape with this angle being less than 109 degrees, 28 minutes, due to the bonding electron pairs being squashed closer together. And it's around 104.5 degrees. That is what it actually gets measured at experimentally. If we have 5 equal things, then rather than 4, around the central atom here, other ones. Those red things are, if you like, in the plane of the page. Then you would have 2 other things, 2 other bonds, like along the z-axis. These ones I'm drawing in purple, up and down. That's the basic structure of how you would separate out to a maximum 5 electron pairs. Right? I'm not talking about bonding and non-bonding. Pretend that they are all bonding. And then if you have 5 electron pairs, bonding electron pairs around the central atom, 3 will be in this plane at 120 degree angles, and 2 will be on the vertical axis there at 90 degrees to the other plane. And if you have similarly 6 different pairs, what do we end up getting? And this shape is called an octahedron. I'll write it there. A triangular bipyramid. Triangular bipyramid. And I will explain why that's called that. That's because, if you look at this, if I point to it here, if you join the apex of the top to these points here, you get a triangle on the base, and that peak there is a triangular pyramid. And of course, there's 2 of these, one on the top and one down below. Hence, we call it a trigonal bipyramid. And you could call this one similarly a square bipyramid. And the square bipyramid is also called an octahedron, or an octahedral shape. Now, Rosie in particular, and everybody else as well, is that making sense? Like the tetrahedron for 4, for 5, it's a triangular bipyramid. Octahedral is when you have 6. And you only need to look up to 6 pairs, right? Rosie, just let me know if that's making sense to you. And if anybody else has got a question. Okay. Now, okay. Then, what happens when some of these are non-bonding? What's going to happen here? Well, let's say, for instance, with the octahedron here, we'll look at this one first and then we'll come to that. With the octahedron here, if we have 2 non-bonding electron pairs, look at this sort of bluish purple lines here, the light purple. on the y-axis. Imagine those are both non-bonding electron pairs. They will stay above and below the plane, and you will end up with a square molecule, a square planar square shape, right? Or square planar shape, all the atoms in one plane. That's if you have two non-bonding electron pairs. If you have only one non-bonding electron pair, what will happen? That will occupy a puffy space on the top, and then there'll be a square pyramid down here because there are 4 atoms here and 1 there. So it's a square pyramid, but it won't be symmetric. It'll be a distorted square pyramid because it'll push these down somewhat to make the angle to the lone pair more than 90 degrees, right? So it will be a distorted square pyramid if it was one lone pair. If there's 2 lone pairs, it'll be a square planar shape with 1 in the center and the 4 at the 4 corners of the square. Okay. Over here, we'll look at what happens if you have one non-bonding pair. The best separation you can have if you have one non-bonding pair is to have it on the, look at this red arrangement of bonds. We'll call that the equatorial and this one the axial. Why am I calling the red the equatorial? I'm saying that the reds are in the plane of the paper, right? So we call that equatorial. They are in the plane of the paper. Those red bonds are the equatorial bonds, meaning they are in the plane of the paper. These purple ones are axial, perpendicular to the paper. Now, look at the axial electron pair. We want to keep the non-bonding, these electron pairs repel each other. If you have a non-bonding electron pair, if it's up here, it will be at 90 degrees away from 3 bonds, right? Which are the 3 equatorial bonds, 90 degrees to each of them. And the other one very far away is 180. But if it's in the equatorial plane, what will happen? It will be at 90 degrees to 2 of them, not 3 but 2, and the other ones are at 120 degree angle to it. And it will squash them closer than 120. So when you have one electron pair in here, the best arrangement is for it to be on the equatorial plane. So if you have one electron pair, it will be in the equatorial plane. And therefore, what will you end up with? I'll draw that in a different color, say in this green color. If you have one non-bonding electron pair, it will make it look something like this to start with, okay? There's the central atom, and here are the other little atoms at the corner of those bonds. That's the big central atom. And of course, I'm just to clarify things for you, I'm going to draw the non-bonding electron pair in the black. As you can see, the non-bonding electron pair is in the equatorial plane, and the bonding pairs, there's going to, oops, that was meant to be in green, not to confuse things. There, we have to go on top of that in the green. There. Okay. Now, what will this shape look like? This shape will look like 1, 2, like a thing there, and these 2. Now, don't forget, these 2 are not going to be exactly along the vertical axis because this is a non-bonding electron pair, which will do what? It will squash these 2 a bit closer together. So therefore, you will end up with a slightly bent thing, which is called a seesaw shape. Because looking at it sideways, it will look like this. There's the central atom. And there. That's called a seesaw shape. Okay, there. Now, that's if you have one lone electron pair. If you have two lone electron pairs, what happens is that they will both occupy the equatorial positions. These two lone electron pairs are going to force these atoms a bit closer together, but it will look basically like a T shape. So that's called a T shape when you have two lone electron pairs on the central atom when the total number of electron pairs around it is 5. So that's going to be a T shape. Why? We have one there, one here, and one down here. And of course, it's going to be a slightly bent T with like this, like a weightlifter who's finding the weight a bit too heavy. It's going to come down a bit on both sides due to the squashing caused by these non-bonding electron pairs. Okay. Now let's look at a quick question with that, and then I can set you some more for homework. We finished. Let me see whether it was on that. Yes. The Lewis diagram for SF4 and XCF4 are shown below. Compare and contrast the polarities and shapes of these two molecules. We'll discuss the polarity. I think I can tell you that quite quickly as well. Now you can see around the central sulfur atom, there's going to be 1, 2, 3, 4 bonding electron pairs and one non-bonding. So what do we start off with as the basic shape? By the way, they don't give you such a table here, but since we have it here, I'll use it. Otherwise, you have to draw it and you have to remember how to come up with these things. So there's 5. The basic shape we start off with is this trigonal bipyramid. Now there's one lone electron pair on the atom, that molecule that we were talking about, which I think was SF4 or XCF4, and therefore it'll end up with the seesaw shape, right? 4 plus 1 non-bonding. 4 bonding and 1 non-bonding. That's going to be the seesaw shape. Where are we now? Let's move to that one there. So sulfur SF4 will be the seesaw shape. Right. And this one similarly, XCF4, you can see that this has 6 pairs around it. So the octahedral arrangement, 2 of them are non-bonding. So this will be the square planar. And as you can see, that's what we had here. And they gave this actual example. There, the square planar arrangement, because the non-bonding pairs are on the vertical axis. So this will be square planar. Right. Now, the symmetry of this, the Xe and the F atoms have different electronegativities, but they are vectors, things with magnitude and direction. Like, think of them as forces. Equal forces along that line cancel each other. Equal forces along that line cancel each other. And therefore, this molecule will be non-polar. On the other hand, look at this one here. This is going to be the seesaw shape. With a seesaw, these things can't cancel out, because if I sort of draw it like that, there's the central atom, and there's the other two. I told you, sort of like a bent seesaw, and there. Okay, there's the central atom. So these things cannot cancel out, the bond polarities, and therefore this will be polar. Right. Compare and contrast the polarities and shapes of these two molecules. So we worked out the shapes, and this one is polar, that one is non-polar. Why is that? Because of the difference in the shapes. This one was an easy example to start with because they actually drew this for us, and that's why I chose that as the first one to go through. I will discuss that in more detail again tomorrow. Now, also do question number 8 as a homework question, very similar to this one here, just with different molecules. Another one. Question number 9. Lewis structure is when you show the shared electron pairs and the bonding pairs. We'll go through that in the answers. No. Okay, just do those ones there. That'll do. We can continue on from there tomorrow. And I look forward to seeing you again tomorrow. Thank you very much for your time. I hope that was beneficial. Thank you very much for your attention and for participating as you have, and look forward to seeing you again tomorrow. Thank you.